Welcome. In this video, we're going to continue our introduction to vibrations and sound. So in this video, we're going to focus on the classification of vibrations into different categories, as well as a procedure for vibration analysis. So first, let's talk about classification of vibrations. There are some important classifications that we can discuss here. So the first is free versus forced vibration. So free vibration is where a system is left to vibrate on its own after initial disturbance and no external forces act on the system. So for example, like a simple pendulum. The key here is that there are no external forces acting and it is just vibrating freely on its own. The other category is a forced vibration system. In this case, the system is subjected to a repeating external force, for example, like an unbalanced motor. An important concept in forced vibration is resonance, which occurs when the frequency of the external force coincides with one of the natural frequencies of the system. And we will discuss this in detail. Another important classification is undamped versus damped systems. So an undamped vibration is when no energy is lost or dissipated in friction or other resistance during the oscillations. Where a damped system is when any energy is lost or dissipated in friction or other resistance during oscillations. So any real system will have some damping, but we do consider undamped systems because they're simpler to deal with, to introduce some of the concepts, and in some cases when the damping is very little, is very small, these can provide a good approximation of the behavior. Another important classification is linear versus nonlinear systems. So in linear vibration is when all basic components of a vibratory system, so the spring, the mass, and the damper, etc., behave linearly. In a nonlinear system, if any of the components behave non-linearly, then we have a nonlinear system. So we're concerned only with linear vibration in this course. Then we can talk about discrete versus continuous systems. So discrete vibration is when the motion can be described with a finite number of parameters, so the displacement or rotation angles. So this, if we go back to when we'd introduced the term degrees of freedom, this means we can have a finite number of degrees of freedom to describe the motion of the system. So these can be solved using ordinary differential equations, these types of systems. The other category is continuous vibrations, where we have a system that requires an infinite number of parameters to describe the system, or infinite degrees of freedom. In this case, we need partial differential equations to solve the system. We can also talk about deterministic versus random vibrations. So deterministic vibration is if it occurs when the value or the magnitude of the excitation, so the force or the motion, acting on a vibratory system is known at any given time. Non-deterministic or random vibration occurs when the value of the excitation at a given time cannot be predicted. And so we're only concerned with deterministic vibration in this course. Here's some examples of deterministic versus random excitation. So you can see in the deterministic one, we have this periodic excitation that occurs, and we can know the value of the force at any time. Where random excitation, we don't have this same behavior. Okay, so let's talk about the procedure for vibration analysis. We can follow kind of the same steps applied to any of the problems that we're going to encounter. So the four main steps are shown here. The first is mathematical modeling. Then we want to derive the governing equations, and we want to solve those equations, and then finally interpret the results. So step one, mathematical modeling. So we try to simplify the problem as much as possible while retaining all of the relevant features. So for example, we can model solid bodies as rigid, we can model the springs as massless, even though they're not. So we need to, in the mathematical modeling step, we basically want to take a real system and come up with a mathematical representation of that. A good rule of thumb is to use the simplest model possible, which captures the behavior of interest. So it's really important to know what we're trying to capture in our model so that we can choose the appropriate level of complexity. So all real systems have at least some mass to store kinetic energy, a spring to store potential energy, and some sort of damping that dissipates the energy. So these are going to be the main elements that make up our vibratory systems. Okay, step 2 is derivation of governing equations. So once we have our mathematical model, we need to derive the equations that describe that. So to do this, we draw a free body diagram and mass acceleration diagrams and apply Newton's laws. So we apply these equations, sum of forces equal to ma, or sum of moments equals j theta double dot. We can use other principles as well, including conservation of energy. We can use influence coefficients. We can use D'Alembert's principle and Lagrange's equations. We just have to use some approach to come up with our equations of motion or our governing equations for the system. And again, these are based on the mathematical model that we developed in step 1. Then once we have our governing equations, we need to solve them. So depending on the type of equation, there are many solution methods that are possible. So there's a standard solution procedure for differential equations. So this is generally only applicable for linear equations, but it's something that we'll use quite often. We can also use Laplace transforms. We can use matrix methods like modal analysis. We can use numerical solutions, including finite element method, as well as other types of solutions. For nonlinear problems, usually numerical solutions are the only thing that is possible. For linear problems, we have a lot more options to be able to solve the governing equations. And what we're solving for is to find kind of the position or description of the motion over time for our vibratory system. Then the last step is to interpret the results. So we need to use the results of the equations to translate the numbers into real physical situations. So it's really important that we remember what the goal of the original problem was. Did we want to find the resonant response? Did we want to find the time to the amplitude of a certain size, the transient behavior, the steady state behavior? What were we interested in the first place? We need to always kind of keep that in mind, especially during the interpretation of the results. And we need to remember the effects of any simplifications or assumptions that we used and where our analysis might not be appropriate if the system inputs change. So along the pathway of solving a vibration problem, we do make some assumptions in coming up with the analytical model or the mathematical model and all these things. So it's very important to keep that in mind, to know what the limitations of the results are, where they're applicable, where they're not, and when we go to apply that to a new situation, can it still work, or do we need to modify our approach?